So in order to have multiple choice 3 completed, I know a lot of you know this, but I want to go over it one more time because it's a silly reason not to do well on this test. How to take the APP1 multiple choice exam, multiple choice part. Okay, first thing you do, lightly bubble your answer sheet from 1 to 36 with all B's or all C's. Okay, so your test sheet should look like this. Yeah, it should look like this whenever you've completed this step. All right, and that should take you like, I don't know, 1 to 2 minutes. Time management is everything on this test. All right, so 2, you want to go through the test booklet. That's just, where the questions are. Up to 36, usually. They might put some filled questions in there, but it should be 36. And circle all of the easy questions, graphs, pictures, etc. Okay, so this should take you 2 to 3 minutes. So this whole section is kind of like just getting stuff situated, approximately 5 minutes. Okay, now when you get to question 131, flip your answer sheet over and look at the bottom of the back page for 131. Okay, you'll know that you're there because one, you'll have flipped the page over, and the gridables that you use for math, you won't use them on this, you won't use any of this, you won't use any of this, but it's right here. It starts at, this is a blurry copy, but it starts at 131. Right here is where you answer the double answer ones. And you'll know you have gotten to the ones that have the double answer ones because it will start off with something that says directions. It'll probably have something underlined that says begin with number 131 on page 3. That's the back of where you normally answer stuff. It is so important that you put these in the right place, guys. Make sure you're paying attention to that. Okay, so this just kind of covers that, what I just said. Here's the thing. You've already gotten all the first ones answered for the most part. So when you get to this one, there is like no pattern of guessing on the 2 question ones. Just start to answer them. You can basically eliminate 2 answer choices and move on. This should take you approximately 10 minutes. Okay, now you go back to the single answer questions. Answer the easy ones first. Be sure you bubble the correct answer and erase your guess answer completely as you go. That's super important. Don't wait till the end because no one's going to grade that like test booklet. Okay, so on these single answers, I would hope that you, out of 36, would kind of be able to deal with, I'd say 16 to 20 of them. All right, so this should take you, remember the test is 90 minutes. 90 minutes. So we're already at 15 off. So I would say that this should take you anywhere between 35 to like 50 minutes. So worst case scenario, you're at 65 minutes right here. Like I said, timing is everything. Okay. Leave any questions that make you feel too anxious. So, that shouldn't be all of them. But, if some really upset you, just leave them. Okay, so then you go back and you count the number of questions you answered with each letter. So I did that up here. I have 5 A's, 18 B's, which was my guess letter, 8 C's, and 4 D's. Okay, so if you have 14, this is if it's a 36 question. If you have more than 14 of one letter, it's usually your guess answer. Go back to that question and attempt to disprove your guess answer. So right here, B's, I would just start going in and you kind of zoom in. You should be able to tell which ones were legitimately B's, like you knew that was the answer, and which one you just guessed. So, or you just left blank. You left as your guess answer. So that would be like right here, right here. I've got a couple here and a couple here. I'd go back and just look for reasons why it's not B and then just go through each letter and do that. It's probably D. I mean, if you've answered everything correctly, but you never know. So also this applies to where you have a run of more than 3 letters. I'm going to see if I have that. And I do. I've got 4 right here. So this would be where I'd start looking at it because that's very unlikely to have 4 in a row like that. So again, you need to have this information at the front of your multiple choice 3 notes for them to be complete. Okay, so now on to the actual multiple choice 3 answers. So in the spirit of you should legitimately answer these things first and look for the directions after I've done all the bubbling in, I would start with the double answer ones. And these aren't as tricky as you think. You can usually eliminate 2 answers. You just have to kind of think about it. Acting out stuff in your calculator and stuff will really help on these. So the first thing I would do is I see something that has an axis looking thing, but that might be a trick. So I circle the labels. I've got K and question mark. So I'm pretty confident in saying this is a graph, but watch out because they want to convince you otherwise. So this says a block is given a short push, then slides with a constant friction across a horizontal floor. So I'm going to start drawing this first of all. I've got frictiony floor. I've got a block that experiences a force, so it's been given a velocity this way. But my understanding right here is it's just given a push and then it's not consistently pushed. And it looks like there's going to be a force of friction acting on the box. That'd be kinetic friction for what it's worth. U sub K. All right. The graph above shows the kinetic energy, not coefficient of kinetic friction, of the block after the push ends, so the push does end, and is a function of an unidentified quantity. So energy versus something else. The quantity could be which of the following. Select 2 answers. So I'm kind of looking at this. It says that the block change in kinetic energy, so that's going down. So basically the block is slowing down. This velocity is changing. And in order for that to happen, it actually has to go some distance or displacement. So I see force and I see displacement. So F, you don't need the dot product, but that would be work. And work can also be a change in energy, which is probably a change in kinetic energy right here. So yeah, let's look for these kind of things. Time elapsed since the push. I don't really know what that would tell you. I don't think it's that one. Distance, I should put an X. Distance traveled by the block. That's up here. That seems important. So I'll put like a squiggly maybe. The speed of the block. Well, kinetic energy and speed ends, so that's kind of pointless. That's an X. Okay, the magnitude of the network. We'll also have work up here because I kind of drew it and maybe acted it out with my calculator or something. So I am pretty confident in saying that it is B and D, and that is the answer. Okay, this one is just like the wording's tricky. A musician stands outside in a field and plucks strings on an acoustic guitar, assuming he's playing a song, or she. Standing waves will most likely occur in which of the following media? Well, standing waves, that's where they resonate. They look like this. You have your harmonics. Basically, that's how you create music. So they resonate. The interference causes them to. Will most likely occur in which of the following 2? The guitar string. Well, that should be like a given, yes, because guitar strings, they're fixed. Whoops. Probably looks like something like that. So that's kind of the whole point of playing notes. Because these are also, when they resonate, these also correspond with notes. Okay, the air inside the guitar. I'm going to go maybe on that one because the guitar is designed to amplify sound. And if you've ever played a guitar or messed around with something like that, you'll feel it resonate if you hit, a note. Okay, the air surrounding the guitar. I put a maybe on this one. I'll come back to that in a second. The ground beneath the musician. That's going to just dampen and cause the sound to go away. So we're going to get rid of that. It's this. Standing waves most likely occur. That's kind of like where are they created. The string, this is a wave on a string. That's what the guitar string does. And then it changes the air around it, which would be inside the body of the guitar. So this one is A and B. These are your right answers. Okay, this is one that you absolutely have to draw, I think. So you got a 2 kilogram rock. It's dropped into a lake from a few meters above. Few. That's weird. You probably haven't seen that as much. Let's do this. This is the lake, and then the rock is few meters. That's weird. There's the rock, and it's gonna be dropped straight down. Okay, so and then it's gonna fall into the lake. So the rock reaches terminal velocity. So you're like, oh my God, no, I don't know what that means. That's okay. It reaches terminal velocity in 5 seconds. So we could put like 5 seconds. Whoops. 5 seconds here, and this would be VT. Let's see if you can figure out what it means just by reading it. During the final 3 seconds, see, you might not even need to know it. In the final 3 seconds, there might be something in between, but 3 seconds, of its descent to the lake bottom, the rock moves at a constant speed of 4 meters per second. And that said constant speed, always look out for that. That means acceleration for this portion is 0. Also, see how I'm using different color pens? That might be useful. You can have a dark blue and a black pen and a pencil. Oh, well, they should let you keep them the whole time. I don't see why not, but maybe. Either way, draw it. Okay, which of the following can be determined from the information given? Select 2 answers. Okay, so the speed, let's just go through them really quickly. Speed of the rock as it enters the lake, maybe. The distance the rock travels the first 5 descent, not sure about that one. The acceleration of the rock 2 seconds before it hits the lake bottom. Well, we already did that. I absolutely know that one is true because I've written my picture. So I go ahead and mark that one. Go to the bubble sheet, bubble as you go. The rock's change in potential energy of the rock earth water system during its final 3. That seems plausible. We've got a lot of information about this last 3 seconds, but let me try and disprove this first one. So it says the speed of the rock as it enters the lake. Well, I could use conservation mechanical energy. I could use sub G, and then which I'd need its mass, which I know, G I know, and then I'd need its height. See, because it goes from potential to kinetic energy. I'd need to know its height, and that says a few meters. That's not going to cut it. So can't be that guy. Okay, the distance the rock travels in the first 5 seconds of its descent into the water. To know this, I would need to know how fast it's going down here. And if I can't figure A out, then I can't figure B out. So that one goes away. So it's C and D. Okay, so this one has this weird little chart and something kind of sticks out on it. The letter E. Now, if you remember, E is the elementary charge, and it can never be smaller. Its magnitude can never be less than 1 E. So you could have negative 1 E, yes. 1 E, yes. Point anything, 0.99 whatever E, no. It cannot be smaller than the magnitude with 1. So I kind of draw this as goes. In the experiment, 3 macroscopic latex spheres, okay, so 3 spheres are sprayed into a chamber, okay, they're in a room, and they become charged with 3E, 5E, and negative 3E, respectively. Later, all 3 spheres collide, so they kind of all get stuck together in one object. So you got 3E, negative 3E, and 5E. So this whole thing's charge would be, let's see, 3 minus negative 3, that goes away. So this whole thing would just be 5, positive 5E. Okay, okay, then they separate. Which of the following are possible values for the final charges on all spheres? Select all answers. Well, first of all, it can't be this 4.5. You can't have half or any kind of decimal involved in this, so it cannot be B. Now, the rest of them, they might not split evenly into 3 parts, and they probably don't because that would give you a decimal. So you're going to just have to basically add these up and see which ones add up to positive 5E. So you've got 4E minus 4E, 0 plus 5. This one's good. Okay, now this next one, you've got positive 5, negative 8, that's negative 3, plus 7, that would be negative 4. Can't be that one, so it's got to be D, but let's double check. 6, positive 6 plus positive 6, 12 minus 7, that's 5. So that's your answers to those. Okay, now onto the single questions, and I'm just going to answer these in order, but you should answer the ones that you think are easy first. A student connects one end of a string of negligible mass to an oscillator, the other to that of a pulley. So on this one, you're basically getting fixed. So that's like closed on a tube and open, or not fixed, whatever you want to call it. The other end of the string is on a pulley. It's suspended to a weight because this is free to move. As shown above, the student finds a standing wave with one antinode. So this is like closed open. You'd know that it starts with an antinode. Sometimes it's easier to draw the tube version of it. Don't do that on free response if it's a string. And one antinode, and it means it has one node. So node is where there's node noise, node sound, and the largest amplitude is at the antinode. You don't have to draw this stuff. I'm just, this is how I think. It might help you. Okay, so that would be the first harmonic when you have like opposite systems like fixed open or closed open. So first harmonic, and that means that its length equals lambda over 4. And that means that, that's lambda. Lambda would equal 4L. Okay, and what are they wanting to know? The student finds a standing wave and it's got a frequency of F naught. The student then moves the oscillator to shorten. So now they've got a shorter one of, let's see, to shorten the segment to half. So this would be L over 2 equals, well, let's just see something. You know what? I got half of the L right here. I'm not going to go through and do all that. You know that wavelength, this is on the equation sheet, equals velocity over frequency. So if I have, I could just change my lambda to 4L. Okay, and let's just compare length to frequency. Looks like they are inversely proportional. So if I have half my length, guess what? Because they want to find what frequency will a standing wave with the first harmonic be found. If I have half the frequency, then I must have double. If I have half the length, I must have double the frequency. Okay, this one's kind of a stupid trick question, but two massive positively charged particles, so I'm going to draw as I go. Particle means round. They both have mass. Are initially held a fixed distance apart. So when we're dealing with these things, we know it's usually r. I'm called distance r. When they are moved further apart, the magnitude of their mutual gravitational force changes by a factor of n. Okay, so basically I see round stuff and I see gravitational. I know that's probably going to be F sub g equals, it's going to be this equation. Okay, and now, so this is Fg between them. So I'll just look at it from here. So this one gets pulled that way, Fg. And then this one would be Fg, and n is just like the coefficient. It's just a number that goes in front of it. So n, Fg. Okay, so they want to know what happens to their mutual electrostatic force charges. And let's see, so the electrostatic force between these guys would be Fe, that's an F, equals Coulomb's constant, charge 1, charge 2, over r squared. It has the same relationship. Like everything's the same but charges. It's just charge and mass. So it would be the same in F sub E. It's going to have the same thing. So they want to know by what magnitude of their mutual electrostatic forces, which of the following, sorry, I wrote over it. Which of the following indicate the factor? Okay, so the factor is the same factor. It would be n. All right. Okay, this is one of those horrible ones that looks like a picture, but it's not. Again, anytime you see like this kind of like perpendicular, could be a graph looking thing, could be a graph, could be a picture, could be who knows what, circle the labels. We got velocity. If it's like a measured thing, especially if it has units, but if it's something you measure, then it's a graph. So we have velocity versus time. This is a graph. So you know, and then when you know it's a graph, you look at slope. So slope is divide. That would be velocity over time would be acceleration. You also look at area. So velocity change in time, be meters per second times second. That is displacement. So that might be useful to know. Sometimes, yes. Okay, so you have a block of mass, and I draw this as I go. Block 1 has a mass of M1. Okay, block 2 has a mass of M2. I don't know anything about them. I'm guessing they're sitting on something flat. And they are sliding together. Oh, so they're like stuck, I guess, along the same horizontal frictionless surface. Oh, no, they're not stuck. That's a weird way to put that. Okay, so they are sliding along the same, okay, and they collide at time t. So they actually started off, one was going this way, one was going, oh, that makes sense. Okay, so block 2 is going negative and it's slower. So it looks like this is like -1 meters per second, and then this one is 4 meters per second. Okay, the graph above shows the velocities of the block as a function of time. Oh, look, and then they have the same velocity afterwards. So afterwards, they're going to end up sticking together and going in the positive direction, 1 meter per second. Okay, so which block has a greater mass based on the information? Which block has a greater mass and what tells you that? Okay, so let's look at it. Block 1 because it has a greater speed before the collision. That doesn't mean anything. That's just like, I mean, anything could be going any speed, so that's kind of a stupid answer. So cross that one out. Okay, block 1 because the velocity after the collision is in the same direction as the velocity before the collision. Maybe. Okay, block 2 because it has a smaller speed before the collision. Okay, again, that's like nonsense. I mean, anything can have any speed. So you can eliminate those two. Block 2 because the final velocity is closer to the initial velocity of block 2 than it is to the initial velocity of block 1. A trick, if you're absolutely stumped, pick the longer one. But let's not do that. Let's actually like figure this out. The same direction, that seems a little iffy. This one's really specific because the final velocity is closer to the initial velocity of block 2. So that means that the bigger one's probably going to stay closer to its original speed. If you need to, act this out with your calculator on your desk, and you will see why. Because if you like crash these into each other, like you're going to see that the base of the calculator keeps closer to its original speed. So the answer is D. Okay, so 4 wants to know how does the kinetic energy of a two-block system after the collision, remember they fused together, compare with the kinetic energy after the collision and why? Well, since they fused together, the whole system would have slowed down, which we saw, and when that happens, that's a perfectly fused equals inelastic, perfectly inelastic actually, collision. And you know for inelastic collision, whoops, K before does not equal K after. So it's got to be A or B. It can't be C or D because it says it's the same. So it's less because the blocks have the same velocity after the collision, like they're together. So some of their kinetic energy was transformed into internal energy. That sounds pretty good, but let's double check the other one. It's less because the blocks had velocities in opposite directions before the collision, so some of their kinetic energy cancels. That one sounds like not such a good answer. I mean, that sounds kind of like childish, I guess. And we do know when they connect, there's like deformation inside of them. So that sounds about right for the internal energy. The answer is A. Okay, so this one wants to know, same thing, same block graph thing. Which of the following is true about the motion of the center of the center of mass of the two block system during the time shown? Well, this whole problem is a conservation of momentum problem, basically, or it could be. So for that to happen, there has to be, it's an isolated system, so no outside forces. That says no outside forces. So that means it's just like the blocks the forces of the blocks on each other. That's the only forces. So it says the center of mass does not move because the blocks, well, we know that's not true because the whole system's moving at the end of this. So yeah, see like how it's moving at the end, so it cannot be, oops, it can't be A. Okay, the center of mass moves at a constant velocity of 1 meter per second because there's no friction acting on the system. Well, that seems pretty close, but we'll see. Let me go back and check the others. The center of mass velocity starts out greater than 1 meter per second, but decreases during the collision because the collision is inelastic. That's not true because, like, with conservation of momentum, they want to know about the velocity. You can lose kinetic energy because it's speed and like it can be going different directions. So I don't think it's that one. Plus, if you look at the graph, there's like no acceleration of the center of mass of the system because there's no outside forces. There'd be nothing to accelerate it. So I don't think it's this one. Maybe the center of mass velocity increases as the blocks get closer together, then becomes constant after the collision. Well, there's like nothing increasing about that graph, so it can't be that one. So if I had to go between B and C, there's no outside forces acting on the system. There is nothing to accelerate the system, is what that tells me. So I think it needs to be constant. So B is your answer. All right, and the last one. This is a graph one. So first of all, let's look at what this graph actually means. We have energy and time. So first of all, let's circle, make sure it's a graph, yes, and we have a circuit. So energy. So let's look at slope, change in energy over change in time equals, hey, that's power. It's on your equation sheet. Also, JJ Watt, change in energy, a lot of work, a little bit of time. And then let's see if the area means anything. So energy, change in time. That's joules times seconds. I don't recall ever having seen anything like that. So the slope is what matters here. And it looks like it's constant. So we're looking at the power in a circuit. The circuit above contains two resistors, R and 2R. Okay, so this is the bigger resistor. It's the bigger 2 PJs in the hall. So the total energy dissipated by the smaller resistance is a function of time. That's this graph. Okay, which of the following graph corresponds to the larger resistor? Well, let's look at this. Power is the VIP room, if you'll recall. Oh, sorry. Potential difference times current equals power. So here is what we know about this. This current splits up right here. And current is inversely proportional to resistance. So you're going to have a bigger current going through the less resistance here and a smaller one here, and they'll join back up. So that means that the current going through 2R is going to be less for current 2. So since power is directly proportional, that's a P, to current, if we have less current, we're going to have less power. So that means the slope of the graph will be not as steep. So we can already eliminate, it's not the same thing, and it's not steeper, so it's going to be one of these. And since it's just directly proportional, we're not going to have to square anything, it's got to be C.